Hello, welcome you all to the lecture number 1 of week 2. As a quick recap, in the last lecture, that is lecture 4 of week 1, we started our discussion by solving some of the questions of practice problem 3. From there, our discussion moved on to the binary codes and their further classification as numeric and alphanumeric codes. The numeric codes were further categorized as weighted and non-weighted codes, and the alphanumeric codes as ASCII and EBCDIC codes. Today we will begin our lecture session by solving one of the questions of practice problem 4 of week 1, and from there our discussion will move on to the topic that will be covered in the lectures of week 2. The question is, represent the decimal number 38 in 2421 code. Show that the code is self-complementing by taking the nines complement. The decimal number 38 in 2421 code is represented as, you can see that tables, the first row indicates the decimal number 38 and the second row indicates the representation of the decimal number 38 in 2421 code. So we can see that the decimal 8 is represented as 110. If you add it up, you will get it as 8. Similarly, the decimal number 3 is represented as 0011. We know that the nines complement of a decimal number is taken as you subtract the number from the decimal number 99, and therefore the nines complement of 38 is 99 minus 38, that is equal to 61. Now we will represent the decimal number 61 again in 2421 code. Here also we have got two rows. The first row indicates the decimal number 61 and the second row indicates the representation of this decimal number in 2421 code. So we can see that the 1 is represented as 0001 and the decimal number 6 is represented as 1100. Representation of the decimal number 61 in 2421 code, we can see that is the ones complement of decimal number 38 represented in 2421 code. Therefore, we can conclude that the 2421 code is a self-complementing code. Now, we will move on to the week 2, what all we will learn in week 2. So, we will start with logic gates. You will know that logic gates made of electronic circuits are used to implement logic expression, also known as Boolean expressions. The logic gates are the basic building blocks of digital systems, and the three basic logic gates are the AND, OR and NOT gate. The logic expressions with the truth table for the different combinations of the two input variables to the basic logic gates are also presented in week 2. The other logic gates that we will study is the exclusive OR and exclusive NOR gates, and the two universal logic gates which are known as the NAND and NOR gate. Thereafter, the Boolean laws and theorems we will discuss, and use of K-map for simplifying Boolean expressions in standard, or we call it as the canonical form, and implementation of this Boolean expression using two-level gate circuits are also discussed. The learning outcome of week 2 lectures will be: first, identify the various types of logic gates, use Boolean laws and theorem for simplifying logical expressions, implement logical expression or Boolean expression using logic gates. So, first we will learn what is Boolean algebra. The Boolean algebra is an algebraic system developed for systematic treatment of logic. When I say logic, it is the binary decision or a logic decision. The algebra was developed by the English mathematician George Boole in between 1815 and 1864. It is defined with a set of elements, a set of operators and a number of postulates or theorems. Unlike ordinary algebra, negative number and fraction do not exist in Boolean algebra. No subtraction or division operations are there in Boolean algebra. The primary application of Boolean algebra is to use in switching circuits. All switching devices has two states, as we know, either the switch is on or it is off. In Boolean algebra, the on state is represented by the symbol 1 or the value 1, and the off state by the symbol 0 or the binary value 0. The symbols 0 and 1 do not have a numerical value. Instead, they represent two different states in a logic circuit and are the two binary decisions of a switching variables, that is true. When I say true, it is logic 1, or yes, logic 1, or false, that is logic 0, or we say no in ordinary terms, that is logic 0. So, we will first start with the Boolean laws. The basic Boolean laws are the OR law, the AND law, and the NOT law, or we call it as the complement law. So, we will start with the second row, A plus 0, that is equal to A. The variable A can have two logic values, that is yes or no, or true or false, or we say as 1 or 0. So, we know that A plus 0 is equal to A, where plus is the operator, and A dot 0, where dot is the operator, is equal to 0, and A complement of complement, that means A's double complement, will give you equals to A. Similarly, the third row, A plus 1 is equal to 1, A dot 1 is equal to A, and if A is 0, then the complement of A, that is A bar, will be equal to 1. Now, we come to the fourth row, A plus A is equal to A dot A is equal to A, and if A is equal to 1, then the complement of A, we call it as A bar or A prime, is equal to 0. And the last row, A plus A bar is equal to 1, and A dot A bar is equal to 0. So, the variable A can have two values, that is 0 and 1, that is logic low and logic high, and which forms a part of the set S. Now, we come to the commutative laws. A binary operator plus or dot on a set S is said to be commutative if A plus B equals to B plus A, or A dot B is equal to B dot A, where A and B are the elements of set S, and A and B can have the values either 0 1 or 1 0 or any possible combinations. Then comes associative laws. A binary operator plus or dot on a set S is said to be associative if A plus B within bracket plus C is same as A plus within bracket B plus C, or A dot B within bracket dot C is same as A dot B dot C within bracket, where the variables A, B and C are elements of set S. Then comes the distributive laws. So, here A dot B plus C, where B plus C is within bracket, can be written as is same as A dot B plus A dot C, or A plus B dot C can be written as A plus B within bracket dot A plus C again within bracket. And the next is A plus A bar B can be written as is equal to A plus B. So, you can use the distributive law. You can write A plus A bar B equals to A plus A bar within bracket dot A plus B. And from the Boolean law, we know that A plus A bar is equal to 1. Therefore, 1 dot within bracket A plus B is equal to A plus B. Then comes the De Morgan's law. A plus B within bracket the whole bar is equal to A bar, or A prime we call A bar, dot B bar, and the second is A dot B within bracket the whole bar is equal to A bar plus B bar. Now comes the idempotent law. We can write x plus x is equal to x, or x dot x is equal to x. Suppose if x is 1, 1 plus 1 will be equal to 1. If x is 0, 0 plus 0 is equal to 0. Similarly, x dot x, if x is 0, 0 dot 0, logic law dot logic law will be logic law. X is 1, 1 dot 1 is equal to 1. Then comes all these laws what we have studied. We can say that the Boolean algebra laws satisfies the duality, wherein the dual of a law is obtained by interchanging 0 and 1 and the operator or and, that is plus and dot, with the variables and its complement remaining unchanged. So, you can see that in idempotent law, x plus x is equal to x. So, the operator is plus. So, if I change it to dot, we can get x dot x is equal to x. In complementary law, we have seen that x plus x bar is equal to 1. So, if I can take the dual of this by replacing the operator plus with dot and replacing 1 with 0. So, what we have seen, that is x plus operator has been replaced, the dual of which is dot, that is, and 1 replaced by 0. So, we get x dot x bar is equal to 0. So, we can say that the Boolean algebra law satisfies the duality. Becomes the absorption law. A plus AB is equal to A. So, we can write that A plus AB using the distributive law as A plus A into A plus B. Okay. So, that will come, or we can write this as A dot B plus 1. We know that from the Boolean law, B plus 1 is equal to 1. So, A dot B plus 1, which is equal to 1, therefore, A dot 1 equals to A. Similarly, A into A dot A plus B, where A plus B is within bracket, can be written as A plus AB, and A plus AB can be written as A dot B plus 1, or B plus 1 is equal to 1, and therefore, it is equal to A. Next, we will come to the truth table. Truth table is a table that contain all possible logical values of an input variable of a Boolean expression. The number of possible combinations is 2 raised to n in a truth table, where n is the number of input variables. We can understand more about it by solving an example. Here, we have to write down the truth table of a Boolean expression. F is equal to A dot B plus A prime or A bar. So, we know that in this Boolean or logical expression, there are two variables, and the two variables are A and B, and these two variables can have any logical values, that is 0 or 1. So, as we know that the number of input variables are 2, and 2 raised to n, which is n is 2, that is 2 raised to 2 is equal to 4. Therefore, there are 4 different possible combinations of the input variables A, B. So, that is shown in the truth table, where you have got the first row, where we had the variables, the first column the variable A, the second column the variable B, and the third column the operation, that is A dot B, the fourth column is A prime, and the last column is A dot B plus A bar. So, we have written the 4 different possible combinations of the input variable AB, that is 0 0, 0 1, 1 0 and 1 1. These are the 4 possible combinations of the input variable A and B. Then A dot B, 0 dot 0 is 0, then 0 dot 1 is 0. Dot operation, we can say it is a multiplication operation. 1 dot 0 is 0, 1 dot 1 is 1. Similarly, we take the fourth column is the A prime, that is A complement. The complement of 0 is 1. Then again we have got A is equal to 0, the complement of 0 is again 1. Then we have got A is equal to 1, the complement of which will be 0, and again we have got 1, that is the complement of which will be 0. Now, our final result will be A dot B plus A bar. So, 0 plus 1, that is the addition operation. I can say the operator plus as an addition operation. 0 plus 1 or is equal to 1, 0 plus 0 is equal to 0, and 1 plus 0 is equal to 1. Therefore, the final answer is, this expression is, for all the 4 possible combinations, we can say that the output value for the first, when both the inputs are 0, the output is logic high. When A is 0 and B is 1, the output is logic high again. When A is 1, B is 0, the input variables, the output is logic 0, that is logic low. And when both the inputs are high, the output is high, that is logic 1. Now, we will come to logic gates. Logic circuits that perform logic and or and not operation are called logic gates. The gates produce a logic 1 or 0 as output if the input signals satisfy the given logic requirement. Boolean algebra is an algebraic system developed for systematic treatment of logic. It is defined with a set of elements, a set of operators, and a number of laws. The primary application of Boolean algebra is for switching circuits. All switching devices, as you know, has two states, either the switch is on or it is off. Now we will come to the positive and negative logic. In positive logic, the voltage level which represents a binary variable equal to logic 1 or logic 0. When the higher voltage represents logic 1 and lower voltage as logic 0, then the logic system is termed as a positive logic. For an example, the voltage level of a variable, suppose a variable A, if equals to its nominal value, say plus 5 volt, then it represents logic 1 or high. Suppose if an input variable A, its logic value is logic 1 or high, or it gives a voltage 5 volt, when we say it is at logic high. If the voltage level of the variable is equal to 0 volt, then it represents logic 0 or low, and we call this logic as positive logic. As you can see that it is represented by a step where the logic 0 represents low voltage, that is it's 0 volt, and logic 1 or high represents plus 5 volt. That is in TTL circuits. In CMOS circuits, it can be, your logic high can be plus 3.3 volt. Now we come to the negative logic. When the higher voltage represents logic 0, that is logic low, and lower voltage represents logic 1 or logic high, then the logic system is termed as negative logic. The voltage value with the logic level 0 is higher than the voltage value of logic 1. You can take an example. The voltage level of a variable, suppose the variable is A, if equals to its nominal value, say plus 5 volt, as per the negative logic, it represents logic 0 or high. If the voltage level of the variable is equal to 0 volt, then it represents logic 1 or low. Then we call it as the negative logic. Now we come to the figure, you can see that logic 0, that is the high voltage, and logic 1, that is the low voltage. That means the logic 0 can be 0 volt and logic 1, that is the low voltage, can be minus 5 volt. We call it as the negative logic. The types of logic gates. The fundamental building blocks of any digital system are the logic gates. The three types of basic gates are the AND, OR, and NOT gate. The inputs and outputs of logic gates can occur only in two levels. The two levels are logic 1 or logic 0. We will first come to the AND gate. The AND gate is a logic circuit whose output assumes logic 1 only when each one of its inputs are at logic 1. We have got the logic symbol of an AND gate. The AND gate can have more than two inputs but only one output. Here we have got an AND gate with two inputs, or the two input variables are the variable A and B. And the output is a single output defined as Z, and Z is equal to A dot B, where dot stands for the AND operation. So we have got the truth table on the right hand side. We have got, because there are two input variables, we have got four possible combinations, and all the four possible combinations are noted in row 2, 3, 4 and 5. And we can see the output values. When both the inputs are 0, the output is 0. When A is 0, B is 1, 0.1, again the output is 0. Then we have got A as 1 and B as 0, 1.0, that is again 0. And when both the inputs are high, logic high, that is 1.1, we get the output as also high. And the next gate is the OR gate. The OR gate is a logic circuit in which the gate output assumes logic 0 when each one of its input are at logic 0. On the left hand side, we can see the symbol of an OR gate. Here the inputs are A and B. Again it can have two or more inputs and can have only a single output as represented as Z. So we can write this as Z is equal to A plus B, where plus stands for the OR operation. On the right hand side, we have got the truth table. We can see that 0 plus 0 is 0, the output Z is 0. 0 plus 1, the output Z is equal to 1. 1 plus 0 equals to 1, the output is 1. And when both the inputs are logic high, 1 plus 1, again the output is 1. So we can see that when both the inputs are at logic low, the output remains logic low. The next gate is the NOT gate. The NOT gate, also known as inverter gate, has only one input and one output. So the NOT gate acts as a complement gate. The output of a NOT gate will always be the complement of its input. So this is a symbol of a NOT gate. We can see that the output, there is a bubble. It shows that whatever the input, we have got only one input. It's a single input and single output gate, the NOT gate. The variable is, the input variable is A. The output Z is equal to A bar, where the bubble shows it complements the input. So we have got can have two values, 0. When A is 0, its complement Z is equal to A bar, that is 0 will become 1. And when A is 1, the output Z is again A bar, that means the complement of 1 will be 0. Then we will come to the exclusive OR gate. The exclusive OR gate is a logic circuit in which the gate output assumes logic 1 only when one and only one of its input is at logic 1. That means if you compare it with the OR gate, you can see that the first you can see the symbol of the exclusive OR gate on the left hand side, and it is written as Z is equal to A exclusive OR B. On the right hand side, we can see the truth table, and we can see from the truth table that 0 exclusive OR 0, that means we get the value as 0. 0 exclusive OR 1, that is the third column, we get the value as output as 1. 1 exclusive OR 0, again we get as 1. And 1 exclusive OR 1, that is the last row, we get it as 0. We can see from the truth table that in exclusive OR gate, its output assumes the logic 1 only when one and only one of its input is at logic 1. Where you can see that in the OR gate, when both the inputs are 1 also, the output is 1. But we have seen that when here in exclusive OR gate, when both the inputs are 1, the output is 0. That means this exclusive OR gate can be used as a parity checker. When there are even number of 1s, the output will be 0, and when there are odd number of 1s, the output will be 1. The next gate is the exclusive NOR gate. The exclusive NOR gate is a logic circuit in which the gate output assumes logic 1 only when all its input are at the same logic level, either logic 1 or logic 0. So we can see the symbol of the exclusive NOR gate. The only difference at the output, you can see a circle, a bubble sort. So we can write Z is equal to A exclusive NOR B. And from the truth table, you can see that when both the input variables A and B are 0, the output is 1. When one is 0, the other is 1, that is the third row, the output is 0. When the fourth row, when A is 1, B is equal to 0, the output is 0. When both the inputs, that is the last row, when A is equal to 1, B is equal to 1, the output is 1. You can see that when both the inputs are at the same logic level, the output is high. That is, when both the inputs are 0, 0, you can see that Z is equal to 1. When both the inputs are 1, 1, the output is again 1. So we can say that this exclusive NOR gate can be used for comparison of the inputs, whether the inputs which are coming to the exclusive NOR gate, whether the inputs are same or whether they are different. So this exclusive NOR gate can be used in comparator circuits. So the exclusive NOR gate, we can say, is the complement of exclusive OR gate. If you compare with the truth table, you can see that the exclusive NOR gate is the complement of exclusive OR gate. Now we will do some of the review questions. We will start with the review question number 1. The control logic to implement a staircase light circuit associated with two switches A and B located at the bottom and top of the stair. So we have got two switches, that is A and B. We can say that the two input variables of a logic gate, and you know that how a staircase lighting operates. When you want to climb up the stair, you switch on switch A, and when you reach the top of the stair or the landing part through switch B, you switch it off. Similarly, while coming down the stair, switch on B, and while climbing down the stairs, on landing, you switch off the light by switching off the switch A. Therefore, we can implement a staircase lighting using an exclusive OR gate. That is, the correct option is D. Next comes, a two input OR gates can be considered as two switches A and B connected in, the four options are series, parallel, either in series or parallel, or all of the above. So when we go through the logic, when we go through the truth table of an OR gate, we can see that when any one of the input is on, we can see that the output is logic high, or when any one of the input is at logic high, the output is at logic high. So therefore, if we want to implement the OR gate using two switches A and B, they should be connected in parallel. The right option is B. The next question, the output of a logic gate is high when all its inputs are logic low. The gate is either NOR and exclusive NOR. The second option is OR and NOR. The third option is NOR and NAND. And the fourth option is exclusive OR and exclusive NOR. The right answer is option C, that is NOR and NAND gate. When you say that, when in a NOR gate, when both the inputs are logic low, the output will be logic high. Similarly, in the NAND gate, when both the inputs are at logic low, the output will be high. Therefore, option C. For checking the parity of a code word, it is preferable to use which gate? So, you have got four options: exclusive OR gate, exclusive NOR gate, third option is NOR gate, and the last option is AND gate. As discussed already, for checking the parities, we use the exclusive OR gate. If the code word has even number of ones, using an exclusive OR gate, the parity checker will give an result as 0, and if it has odd number of ones, the output will be 1. The number of rows in a truth table having 4 input variables is, the four options are A4, B8, C32 and D16. So we have learned earlier that if the number of input variables is n, then the different possible combinations is 2 raised to n, where n is the number of input variables. Here we have got 4 input variables, therefore 2 raised to 4, therefore the different possible combinations are 2 raised to 4, that is 16, and the last option is the right option, that is answer is D. The output of a NAND gate is low only when all the inputs are logic high, all the inputs are logic low, or at least one of the input is logic high, at least one of the input is logic low. So NAND gate, we know that it is the complement of the AND gate. So therefore, in AND gate, when all the inputs are logic 1, when all the inputs are at logic 1, suppose it is 1.1, then the output will be 1. So therefore, the complement of that 1 will become 0. Therefore, we can say that the output of a NAND gate is low only when all the inputs are logic high. That the right option is answer A. So there are some practice problems. I have given it as practice problem 1. Practice it, and if you have any doubts, we can discuss in the next class. In the next class, we will be solving some of the problems of practice problem 1. Thank you and see you in the next lecture. Until then, goodbye, happy learning.